I'm Ryan. I'm one of the co-founders of Vals AI, and we benchmark large language models on real-world tasks. So we have a bunch of work in legal and finance, and I've been a big fan of John for some time now, and we've hosted a SWE-bench, which is one of the most important benchmarks in the industry, and really has driven a lot of progress that we've seen in the last 12 months. And so with that, I'm very excited to introduce John. And as a quick format, we will have 30 minutes for John to give his talk, and then we'll have an open discussion QA format where I'd encourage people to use the QA button in Zoom, not the Zoom chat, and then we can go through those, unmute people, and have them in an open conversation. So with that, John, take it away.
Cool. Thanks, Ryan. Yeah, I really appreciate you guys having me here today. It's such a pleasure to be able to talk to such a wonderful audience. So, yeah, hopefully I do justice to the invitation, but nice to meet everybody. So, yeah, I will share my screen really quick. Oops, I shared the wrong screen. Sorry, one second. Share desktop too. Okay. And then hopefully everybody can see my screen. Okay, awesome. All right, okay. Yeah, I'll be mindful of the time. It's like 11:06 on my end, so I'll try to wrap it up by about 11:36. But yeah, please feel free to, ask questions as they come up, but I guess we can leave them towards the end as well. But yeah, so today I'm super excited to introduce essentially like a suite of works that I've been doing across the past 2 years. Starting with SWE-bench, which hopefully a lot of people are fairly familiar with it at this point, but I'll kind of speed run through that, just given that people are using it, and hopefully there's not too much explanation needed on how it works. And then I'll talk a little bit moving into sort of, given this evaluation, how did we actually get this V0 SWE-agent thing to work pretty well? Work pretty well means getting language models to actually perform well on this GitHub resolution task. And I'll kind of talk about kind of the interesting developments that happen after we release that project. And then very lastly, I'll conclude with the most recent work, which is a paper called SWE-smith, which is now that you have the evaluation and the agent scaffold, how do we actually try to build good software engineering language models in the open? And I think I'm very excited about, where we could be in a couple months to a year of just having, free open data, open weight software engineers. Yeah. Cool. So starting with the first paper, which is SWE-bench. Yeah, I'll go through this pretty quickly, and I'll try to keep the history a little bit more interesting as opposed to, just repeating what's in the paper. So prior to this work, this is around like mid 2023. At the time, I think the big benchmark at the time was human eval. And you had, a lot of these kind of code completion tasks where I gave you a method header and I gave you some sort of doc string describing like what exactly the method should be doing. And the goal of the language model is to produce some completion or implementation to the function that achieves, the desired functionality. So pretty straightforward, like lead code-esque kind of stuff. But with our sort of 2025 hindsight, we can confidently say, those questions are kind of interesting, okay, for like passing interviews, but the utility is fairly limited, and there's a lot of disparities between that setting and sort of what you and I might do on a daily basis in terms of software development. So the inspiration at the time, and I do want to give a lot of credit to my co-first author for two of these projects, Carlos Jimenez. We were both at Princeton at the time, and we thought like, hey, like repos seem to be kind of interesting. There's a lot of context in repositories. It's like much more real world. And wouldn't it be interesting if we could identify some sort of task formulation that requires a model to like execute the code base, kind of play with it, toggle things to sort of solve a set of unit tests? And what really occurred to us very quickly after that was that if you go on GitHub, and I think this is sort of like pretty obvious the moment it hits you, is that there's this sort of issue PR dynamic that goes on, right? So if you're a maintainer of a code base, someone comes to you and they post an issue on your GitHub saying, hey, something is broken. This is the behavior I'm expecting, but this is what I'm seeing. Sometimes they'll add a little bit of code to reproduce the error, or they'll give you some sort of stack trace representing the problem that they're running into. And you're going to take that issue as a maintainer, you're going to take a look at it, and some of the time you're going to decide, hey, this is worth working on. So I'm going to iterate on the code base, I'm going to fix the bug, blah, blah, blah. And then I'm also potentially going to add some tests that are going to make sure that that bug doesn't occur going forwards. You create a PR for it. Maybe there's other people that review it, but then you merge the PR and then the issue is closed, you know? So there's this sort of very healthy kind of like report a problem, resolve the problem dynamic. And for us, like it became sort of inspiration of why don't we kind of turn this real world pipeline of collaboration into a lot of these cool task instances that we can use to evaluate language models. So that was kind of like the sort of the moment of inspiration. And this is just to kind of visualize that very briefly. But that's pretty much, once we had that idea, it really took off. So we thought about it, it really made sense within like a day or two. And then Carlos and I were kind of off to the races, and we just started like coding up SWE-bench. Like, and I think we had like the task instances, the benchmark, like within a month. And so the workflow was pretty straightforward. So just to kind of ground it a little bit as a reminder, like the idea is that you give a language model, or you give, you know, an AI system, generally speaking, both the code base along with the GitHub issue text. So someone pointed this out on Twitter like a week ago, but this is an actual real example from scikit-learn. And there is like this is like a real issue. I forgot what the issue number is, but you know, it's probably saying something about, hey, you know, this method is broken or blah, blah, blah. You know, the language model is given the issue, it's given the code base, and you know, what given a code base means will actually change over time, as I'll explain later. But the language model will take these two things, and the ultimate goal is that it generates a PR. So pull request in practice concretely actually means like a diff. So, you know, every time you do a git commit and you do kind of a git diff or something like that, like really that kind of file format where the diff represents a set of changes or modifications to the code base. And then last but not least, once you have the diff, you know, you take the unit tests that were associated with that pull request and you run those unit tests against the language model solution to check whether the model solution actually solved the issue. So that's the general task formulation. Hopefully people are fairly familiar with it at this point. A little bit of the magic is in more of like how we actually put together this data set, which these days, you know, after SWE-bench, things like SWE-bench Pro or SWE-bench Live or SWE-bench Multilingual, which we did, and the multimodal version, or even multi-SWE-bench from ByteDance. I think there's it's been great to see kind of a lot of iterations on this task pipeline. But generally the way it works at its core is you kind of pick a repo and then you just scrape all of the pull requests, and you identify the pull requests that are associated with issues publicly. So what you end up with at this first sort of left-hand most column after you run that is for every repo, you have a bunch of issue PR pairs. And those are just kind of like the raw forms of the issue PR pairs. The criteria that you're looking for that these pairs satisfy is first that the PR is associated with an issue, and then that issue essentially constitutes your problem statement at the end of the day. And the other main criteria is that the PR should be editing or adding tests to it. And the heuristic is actually pretty simple. Like if you have a PR, you take a look at the PR, you identify like via the file paths. If the file path has the word test or tests or testing in it, that's usually a pretty good sign that like, you know, this is somehow related to unit testing. So then you can essentially split that diff up into the testing portion, which you're going to run later as part of like the right-hand most side here of like running unit tests against the PR. And then the non-testing part is essentially like your reference solution of like, how did the real world kind of maintainer actually solve this issue. Yeah, but after you have that, the toughest, trickiest part of SWE-bench was doing this kind of execution-based filtering. So what this means is that for every task instance, you want to be able to create an executable environment, which effectively really just means a Docker file. The Docker file has the code base in it checked out to the commit right before that PR. So, and then it also has that code base installed. So there's a couple steps, but basically, to put it very simply, the goal is that when you can give a language model this environment such that it could interact with the code base to try to solve the issue. But yeah, anyway, we were able to kind of like feed a lot of issue PR tasks through this kind of filtering and then the execution-based validation. And what we ended up with were 2,294 task instances across 12 repositories. So interestingly enough, like the latest, the most widely used SWE-bench variant these days has and continues to be SWE-bench verified. SWE-bench verified is actually a 500 task instance subset of the original 2,294. And this was kind of put together via collaboration with us, me and Carlos, and the OpenAI team, like the preparedness team specifically. But yeah, not to jump too ahead too quickly. So this is kind of like the form factor of a typical SWE-bench task instance. You have some statistics here. At the time, what we did was before the craze of like software engineering agents or these kind of fancy workflows took off, what we did was a very simple RAG-based system where we indexed the code base. The problem statement became the query for picking out like which files were relevant to edit. And then we trained something based on Code Llama at the time to actually generate a diff directly from entire files. So this was like a very, very sort of simple, didn't work that well, but kind of like the most obvious solution at the time. So you can imagine that like the solution did not work particularly well, and at the outset of SWE-bench, performance was really, really, really low. So BM25 retrieval just means for a RAG system, this was the indexing engine that we used at the time. We also had this Oracle retrieval setting where we just assume like, okay, if you have a perfect RAG system, which means we just give it exactly the files that the gold solution edited, how much does that actually help performance? So these percentages are out of 2,294. So it was very few instances. But at the time, it was actually quite exciting to see that, like, okay, there's this like very, very minor portion of real world software engineering tasks that like models can technically replicate. Yeah. Cool, but that's pretty much the gist of SWE-bench. We had some insights at the time that still continue to hold true. Like, you have some repos that are more difficult than other ones. This long context issue, I think it's been addressed a lot more in the recent months. But about 2 years ago, this was when the paper of like, lost in the middle and kind of needle in the haystack was really trending at that time. And so we dedicated some emphasis of like, this is a truly realistically long context benchmark where you're dealing with a large code base where you're not necessarily having to edit a lot of it. So localizing which files to actually change was kind of a big challenge at the time. So yeah, that's pretty much SWE-bench. I mean, it's kind of taken off at this point. Like if you're interested, like we have the leaderboard, we continue to maintain it till this day. This is the full SWE-bench split. People have from time to time evaluated on it, but as you can see, like the verified split is a lot more popular. When SWE-bench initially came out, the original numbers are still there. But numbers have really skyrocketed in the past couple months. Like when verified initially came out, these were the numbers that we were working with, and it's kind of incredible to kind of see that steady trend line going up towards like, I guess like, I think Claude 4.5 Sonnet recently reported that they got 77% pass at one, and then like northwards of 80% with some sort of like test time scaling mechanism. So Yeah, this number has been going up. The one question that people have posted, like just in general, is like, is SWE-bench verified saturated? I think we're close. Like I think the fact that it's gone from like 10% to 80% is pretty incredible. The one number I will concretely say makes me feel like there's still a little bit of room to crawl in SWE-bench is that if you aggregate all submissions that have ever been sent to the SWE-bench leaderboard that we maintain, which is really represented by this repository here. And at this point, like for the verified leaderboard, we have like northwards of 100, but I think closing in on 200, maybe even closing in on 300 submissions total. So if you look at like all 300 submissions and you look at like what percentage of 500 task instances were ever solved by any of the submissions, that number is actually 92.6%. So there's still kind of like 10 percentage points higher than sort of what people are reporting right now. The next question you might ask is like, well, are a lot of these submissions just like that instance got solved once ever, or was it multiple times? So if you make the criteria a little bit stricter of like, out of all submissions ever, how many instances were solved by at least 4 submissions, that number is still like 89%. So I don't think these instances are being solved as kind of like one-time flukes, or, we have a pretty good system in place to make sure that the submissions are reliable and there's nothing fishy going on. So, if you're still interested in pushing the frontier of SWE-bench, I think there's a tiny bit of ways to still go with a verified. And, with some of the more recent data sets like SWE-bench Pro or whatever, like there's a lot of room potentially to climb. But cool. Okay, I realize I'm spending like half of my time on SWE-bench and that there's more interesting things to talk about. So I'll try to speed it along, but we can answer any questions later on. So the next project that I focused on in this series was this project called SWE-agent. So the impetus for this at the time was I had done this prior work called Inner Code about a year ago. And the idea for Inner Code at the time was that a lot of these code completion benchmarks like human eval or like NL to bash at the time, which is, if you're aware of that paper, it's like OG terminal bench essentially. And a lot of those, the task formulation there was like, give the language model the question and then have it directly generate the output. And so the intuitive thing to do was like, okay, well, why don't you give a language model a terminal or like a CLI to interact with? And so at the time, what we did was we took a lot of these existing data sets, we built environments for them, like very simple Docker files, literally just using like the base Ubuntu or like Python 3 images, and then just putting together the logic to actually have a language model issue commands to the terminal and then receive output. Granted, the task instances were a lot simpler than SWE-bench and terminal bench, but at the time that was a meaningful step forward. So the immediate question that we asked was, well, why don't we kind of take SWE-bench and put it in this interactive formulation where a language model is issuing bash commands, getting standard output as feedback, and then sort of interactively modifying a code base towards solving the problem. So we tried this, and keep in mind at the time, the cutting edge models were kind of like GPT-4 had just come out, we're still dealing with like Chat GPT like 3.5, stuff like this. And what we found was that this kind of interact with the terminal paradigm was quite out of distribution for these models at the time. Like, I think they were just fine-tuned or post-trained or whatever you want to call it to be chatting with a person. And so if you told it like, hey, you're interacting with a terminal environment, these are the things you need to do, it wasn't very sort of like intuitive for the model to perform well in that setting. And so I think this inspired this general idea of like, okay, the middleware that is sitting between a language model and environment can actually be designed meaningfully to improve language model and performance within the environment. And this is sort of, this middleware is we ended up giving it a name, which is like agent computer interface. And the high level concept here is really just like highlighting that shaping the way a language model interacts with the terminal is sort of like can have meaningful impact on downstream performance. So I'll go through what we did in this paper, but then I'll comment a little bit more on like how well this has held up in today. So what we did at the time was like really, we found SWE-agent, it was struggling, or language models were struggling with just issuing straight bash actions. So we built it kind of like in terminal, like file viewing, file editors, instead of making it do like find or greps. And we found that with find or greps, it was kind of really struggling with like parsing those results in sort of more refined ways or adding filters on top of it. Instead of those, we built like search tools, and ultimately bash was still available, but mainly file editing and search were kind of two things that we really heavily designed. So you can kind of see this in the paper if you want to read about it very thoroughly. But this is an example. So as an alternative to like a cat, where a cat piped into a head where you view the first 100 lines, we really built this tool that made it a lot easier with respect to kind of the behavior of language models at the time to view specific parts of the file and also give it sort of additional context. So like telling it sort of the path was important, the total number of lines in the file was important, the window size, like in here it's looking at 30 lines at a time, but sometimes you want it to be able to let it adjust to looking at 100 lines, or adjusting the size of the window, its ability to jump around in the file. That was really important. Editing was a big thing at the time. So if you look at bash and you have some familiarity, if you're thinking about doing bash only editing, then like SED is kind of the go-to command that you would use. And we found that it struggled a lot because with SED, what you need to do is do a good job of rewriting the part that you actually want to replace in the file. And we found that language models made a lot of kind of tiny mistakes there. And so you had these kind of cascading failures of just wrong SEDs, like failed SEDs in a row. So based on that, what we did was like we created this kind of edit function where you would specify the line numbers to indicate the block of code that you wanted to replace. And then what the language model would generate is actually just like, the code that it wants to replace that block with. And then we added some linting. So all of these sort of like small designs were super helpful. And then also kind of like shaping the context. I mean, I think each of these parts independently have kind of like grown into much bigger systems that people have built. But yeah, SWE-agent came out, and then like coincidentally at the time, Cognition had just released Devin, and SWE-bench was kind of the benchmark that they highlighted at the time. And basically, they released, Cognition released Devin in March, SWE-agent came around in April, and it was just 1% off from what Devin was reporting at the time. So there was a lot of concurrent work early on for SWE-bench that was still focusing on the RAG system. But once we had this proof of concept that your agent, this kind of agent React style setup works pretty well, that kicked off like a lot of exploration around software engineering agents. So beyond Cognition, like I think a lot of the startups that people you might be aware of today, like Factory or kind of everything that you see listed on the SWE-bench leaderboard, like Warp, it was great to see. Like I do think like SWE-agent was kind of the open source starter kit for kicking off like a lot of that investigation of like what tools matter, how do you shape these tools, if you're managing context or agent memory, kind of like startups like Letta do, what are certain things that you can do there. So there was this big arms race of like, let's improve the scaffold as much as possible. And I would say that this led to a good amount of improvement like early on. So I think like if you kind of organize by the dates around when SWE-agent came out in like mid 2024, like April of 2024, you got a lot of submissions in the coming months of like we added this tool, we made context management better. We added this kind of like guardrail that, addresses this weakness in the agent, and you kind of saw incremental climbs in performance, So, yeah, that was the exciting part about SWE-agent. I think it just served as a precedent for kind of a lot of the agent-oriented systems that you see today. And then I think okay, I'm a little bit low on time, so I'll spend the last 5 minutes just going through SWE-smith really quickly. And the inspiration behind SWE-smith is following this kind of leaderboard. A pretty big moment internally to us, like the SWE-bench team, which was kind of me, Carlos, and then Ophir and Killian, was that around, I want to say, August, or here, let's see where. Yeah, right, August, or yeah, October, probably like a year ago, when Anthropic released Sonnet 3.5. That was the first time where, we had a little bit of discussion with them, and we found out like they're not actually making the tools or making the scaffold super complicated. They just have a better model. Like 3.5 is just objectively a better model at SWE-bench, at agentic coding than prior models. And after that came out, I think that started to inspire this sort of new investigation into like, okay, you have the agent, you have the evaluation. From a model training perspective, like what is going to make models better at software engineering agentic coding? And I think the pretty obvious answer, like intuitive conceptually, was to do data. So by data, what we mean is kind of like there's a lot of repos out there. SWE-bench is an evaluation set of just 12 repositories and 2,294 task instances. If you're going to try to create a training set, ideally you're training on a lot more repos and a lot more task instances. And at the time, there were kind of like two threads of work. So SWE-gym is kind of the earliest like SWE-bench training set. Pretty much what they did there is just redo the SWE-bench training pipeline for another 11 Python repos, and then just designate those repos as training repos and the SWE-bench repos as test repos. It was a good initial work. I think a lot of the initial results were pretty exciting. But if you look at the data size, it's identical to SWE-bench in size. And so if you want to train a model that's going to be really capable, you're going to want to go like orders of magnitude larger than what they have featured. Another alternative was that there was this kind of line of work around like agentless solutions to SWE-bench. So don't do interaction, don't do agents, just kind of have this workflow where the language model is never gonna have to actually execute any code. And it's just gonna sort of like solve the software engineering problem, almost like a math problem where it's like reasoning very heavily over it. The companion data sets for this were, let's scrape a lot of issue PR pairs, so kind of like the first half of SWE-bench collection, but we're just going to skip over the part of creating execution environments for them. I think now in 2025, it's quite obvious that a lot of people care about execution. There's a lot of value in extra signal and extra tokens and training data you can get from it. So I think like both of these strategies at the time were pretty straightforward descendants of SWE-bench, but they ran into the limitations that the original collection pipeline had, which is the difficulty of constructing execution environments and also just the manual labor associated with like, scaling these things up, right? So SWE-smith is kind of the answer to this. So just to highlight, like there's these kind of three critical pain points with SWE-bench. And what we did, SWE-smith is really our effort to overcome it. So the idea in a nutshell is that I take the latest version of a repository, I create just one execution environment for that version of the repo, but then using that repo, I apply a lot of strategies that will create changes in the code base that break existing unit tests. So just to kind of put it very simply, I take like some Python repository, I run PyTest in it, I do installation, I create a Docker environment, I can see that it has like 250 passing tests or something like that. Then what I do is I apply a suite of these task generation strategies. So for example, we can take a function, convert it to an AST, and then randomly modify that AST. So abstract syntax tree. You remove assignments, you flip operators, you screw up the conditions in, ifs, or mess with the looping mechanism of a for loop. And then you recompile that AST back into source code. And what you have there is a completely free, like no cost, not using a language model way to create a bug in the code. And then you just check that, by rerunning the existing test suite, does one of the existing tests that was passing, does it break? So essentially you're doing reverse SWE-bench in this case, and you get a lot of task instances that way. We suggest a bunch of other strategies. You can use a language model to generate bugs as well. You can kind of merge patches together to get bigger and more difficult bugs. Last but not least, to make it kind of backwards compatible and like grounded in real world, you can also undo PRs in the latest version of a repository, right? So all of these strategies allow you to take one repository and just create one Docker environment for it and synthesize hundreds to thousands of task instances per repo. And the scaling factor is just going to be way better than SWE-bench collection. So with 128 repositories, and with 128 repositories, the part I kind of skipped over is that using a language model, we were able to kind of automate the execution environment installation procedure. So, it's not 12 repos, it's 128 repos. It's not 2,000 something task instances, it's now 50,000 task instances. We're going like an order of magnitude higher for both repos and task instances. And you get this really rich data set. And this kind of comparison of SWE-smith with any of the SWE-bench related training data sets these days. So there's a lot of advantages. Not only is this higher, but another good thing is that the total storage size required for the Docker images to train on is magnitude smaller than any of the other data sets. And this is related to the fact that we create a Docker image per repository and not per task instance. It's a finer grained detail. If there's questions, I'm happy to answer more, but it is quite meaningful. So just to kind of wrap things up really quickly, we didn't do RL at the time. People are using RL to do SWE-smith now, but we just kind of did distillation, fine tuning at the time. We took a subset of the 50,000 task instances, ran SWE-agent with some of the cutting edge models at the time, which was like Claude 3.7 and GPT, and we generated a bunch of trajectories and then fine tune on them. And what you see is that, the performance gets really good. It goes from, the base model was Quen 2.5 coder, 32B, and you go from like 8% to 40%. Just to highlight like a couple interesting projects. So this is our table, and this is really just May, which is a couple months ago. But some of the really cool projects is like, I've seen mini coder. So this great researcher, Ricardo, what they did was they took mini SWE-agent, which at this point, if you're not aware of mini SWE-agent, you should totally check it out. I can explain more later on. But they took mini SWE-agent, used Quen 3 Coder 30B as like the teacher model, and then used SWE-smith and mini SWE-agent to generate 400,000 trajectories. So just to give a sense of scale, for SWE-smith, we only did 5,000. They did orders of magnitude more. And you have like a 1.7B model, which is tiny, getting 18.6% on SWE-bench verified, which as of a year ago, I think this would have been unthinkable. You have a 4B model, 26.8%. If anybody in the crowd is like an RL expert or kind of wants to do post-training and is looking for kind of an easy win, I would just say if you could set up RL execution environments for SWE-agent to run with this, just run it on the model that they've already fine-tuned, and you could get like a 4B model that's scoring like 40-50% on SWE-bench verified. I think I think it will happen. It's just like a matter of time. But yeah, anyway, closing things out, we did a bunch of interesting things, like people are using SWE-smith for fine-tuning, for RL. The main effort that I'm kind of focusing on right now is to increase the number of repos and task instances. I am still focused on the data. So SWE-smith used to be 128 repos of Python, and so everything was Python. We've already expanded to 100 more repos of Go, and we have 10,000 Golang instances now. And I'm just, we're really just trying to expand to like more languages. So, I mean, I think the upshot of all of this is that there's a lot of great evaluations out there. For if you're doing research into software engineering agents, I think if you're just interested in coding agents as tools, by all means, you should use Claude Code, you should use Gemini CLI, you should use, Codex, Cursor. These are all fantastic tools that are much more performant. But if you're interested in doing research on coding agents, I'd really recommend kind of looking into this kind of ecosystem. We put a lot of time into maintaining it, evaluating on SWE-bench, using SWE-smith as data, and then using mini SWE-agent, which is a great scaffold for language models interacting with code bases. And using this ecosystem, you can generate a lot of great artifacts as training data, as sort of like post-training infrastructure. And who knows, I think in a year, maybe you have a 7B model that's scoring like 50-60% on SWE-bench verified. Maybe we enter an era where everybody has open data, open weight software engineers, where you're not paying subscriptions anymore. And I think if there's more investment in like open source research for software engineering agents, like I think there's a very exciting future where people are just running local 7B agents that can do incredible things on code bases. So with that, I'll kind of conclude my presentation. I went a little bit over time, but hopefully that was interesting. Thanks again.
Thank you so much. That was awesome. A lot to unpack there. Thanks, John, for the talk. People can start putting their questions in the Q&A feature, and then I can unmute you one at a time, and then we can go through that. Maybe just to seed the conversation, I'll also start by asking some questions. Maybe one that's just kind of an open-ended one. You talked a little bit about how there's been kind of an iteration where harnesses yield improvements, but then something like Sonnet 3.5 comes out, just a strictly better model, which results in better performance. And maybe mini SWE-agent gets at this as well, but do you imagine we'll see continued improvements at the harness level or at the model level, or some combination of both?
Oh, that's a great question. To answer it straightforwardly, I think I'm more bullish about the model level right now. I think with the frontier models, just yeah, I think you make a great point. So just to kind of point things out, to introduce mini SWE-agent properly, with SWE-agent, we had like a bunch of tools, a bunch of sort of like, edit tools, file edit tools. What we found like a year later was that models don't actually struggle that much with Bash anymore. I think that's probably like the most significant change that occurred to us. So what we ended up doing, and this is totally the labor of one of my great co-authors, Killian Liret, but Killian ended up taking SWE-agent, getting rid of all the tooling stuff and just focusing on facilitating good Bash only interactions between a language model and the command line. And if you look at so we have this mini SWE-agent like Bash only leaderboard, which basically is just every model that comes out run with mini SWE-agent. And mini SWE-agent, it doesn't have tools, it doesn't have anything, it's purely just Bash. You can see like the numbers are incredible. It's certainly 7 points off from what Anthropic reported with their, tool set. So I'm sure whatever they're doing, like there is a 7-point differential. But if you look at the gap between like a model versus like toggling the scaffold versus you keep the scaffold constant and you vary the model, the difference in performance is much more significant for when you keep the scaffold fixed and then you vary, which model is being used. So yeah, I'm much more bullish about like making the models better as opposed to the harnesses at this point in time. Yeah.
Got it. Makes sense. That seems also consistent with what Mike Merrill was saying last week as well.
Yes. Yeah.
All right. Looks like we got some good questions coming in. So Mihail, I'm gonna ask you to unmute so you can ask yours, and then Kelly, you'll be coming up next.
Sure. Can you guys hear me?
Yes, we can hear you.
Cool. Well, first of all, thanks, John. Really appreciate the talk and also a lot of phenomenal work. I mean, SWE-bench really, I think, did pioneer a lot of what we today call modern agentic systems. So, super appreciate the work you guys have done over the last few years. Um, my question, I have two, but I'll start with one and then hand it back to the room. You mentioned this idea of like the scaffold versus the model, right? Being like the two levers that you can kind of maneuver and kind of play with to improve performance. I'm curious whether you've seen any sort of breakdown of like what error modes still exist that are the hardest for the best systems today to do well on. Like in the sense, has there been sort of like a taxonomy of complexity, engineering problems or complexity classes, the where we can do like really, really well on single line functions and maybe like the smallest, maybe the easiest kinds of PRs in like the SWE-bench suite, but maybe like multi-line, certain kinds of architectures that are still really hard to tackle. Just curious whether you've seen any work on that or have investigated that yourself.
That's a fantastic question. Yeah. There's one archive paper. I'm not sure if I'm gonna be able to find it. I really hope. Okay. Yeah. I think the closest I've seen comes to this one where I think these guys did really great work where they honestly just dove into like the experiments repo. And so the great thing about experiments is everybody that submits has to upload trajectories, and of course they have to upload like the diff that the model actually came up with, and they kind of deep dived into the trajectories, like the form factors of the changes. They did some categorizations. There's some other papers, but I would say like this one feels quite complete from what I've seen. But I think some of the general conclusions I've seen is SWE-bench verified is curated. The curation was kind of interesting, where if you look at the distribution of the problems compared to original SWE-bench, it is easier. I do think verified, out of every split that we've created, verified, light, and full, it is for sure the easiest split of SWE-bench. So what that means is like, if it's getting 70%, a lot of the problems are like not only single file, but also single function. So if you look at sort of the arc for solving a lot of the problems that are represented in verified, I would say like more than half of them are easily just like the issue is already kind of suggesting like where the fix should be. You go there, sometimes the stack trace or the reproducibility code will even have the function name, and then it'll just go and it'll kind of like do the fix, and then use kind of any reproducible scripts in the issue to solve it. So I would say like I think with verified, localization is arguably a little bit too like it's a little bit too easy, and that the issues were curated such that this information was available. The challenge of like reasoning about, okay, given this kind of issue that's still complete in a sense that it is showcasing the error, but it's not obvious or it's not made clear where exactly in the code base you should be editing. Those task instances are in SWE-bench full, but they unfortunately just got filtered out by the verified process. I mean, I guess not unfortunately. I think at the time, because performance was poor, like there was really, kind of a lot of care and attention towards like how do we curate a subset that is worth focusing on. So I should amend that and say, fortunately, we have verified. But I would say like now that verified performance is getting a lot higher, like, we can kind of refocus on like what is the decision boundary, or what are sort of the when we're curating tasks that we care about solving, like we can kind of like rethink like, okay, we've moved past this easy stuff. How do we identify the next set of meaningfully hard stuff? So to answer the question, I think what the types of problems that fit like meaningfully hard is the next step. I think like task instances with problem statements or issue text that is not necessarily fully specified in a way where the things that are omitted can still be discovered in the code base, but it requires some extra exploration. I also think just like benchmarks that are more representative of like a larger spread of repos, I think that's been done already to some extent. And I think the last thing that's quite obvious is just like, if you look at correlations, performance still correlates very heavily with like the size of the reference solution. Like if this was a PR that required changes to a lot of files, had a lot of tests that were introduced to verify these changes, these task instances are definitely a bit more difficult. But yeah, I mean, like beyond just curating like larger diffs, I think just thinking about how to curate the right mix of SWE-bench style task instances could be interesting.
Okay, great. Kelly, I'm gonna ask you to unmute. Do you wanna ask your question? Okay, I'll ask it on her behalf. What do you think are the key differences between terminal bench and SWE-bench verified?
Oh, I think, yeah, I mean, I think they're both great benchmarks. Terminal bench is curated in like a completely different way than SWE-bench. So SWE-bench directly grabs task instances from kind of real world PRs and issue pairs. Terminal bench requires a person like sitting down and like basically coming up with a problem. So I would say like I think the form factor is probably quite similar in that terminal bench still uses like here's a Docker image, here's some scaffold to facilitate language models interacting with the terminal. So I think like the modus operandi of like how language models solve the problem, that form factor is still the same, but I think where the problems come from are quite different. Terminal bench is great. I think it's a fantastic benchmark. I think it would just I think the authors are in the process of like scaling up evaluation. I think the initial V0 had like 70 something task instances, and I think they're trying to push it to 100 right now. The task instances look super different. I think you still have a lot of task instances that are software engineering and terminal bench, but even within those, you have some that are like very long running. Maybe you have machine learning ones. Like I think in the paper they mentioned that some of these task instances are supposed to take hours at a time. So I think they're both cool benchmarks. I think they both kind of test a similar form of interaction of language models interacting with the code base. But yeah, I would say like the problem source is probably the biggest difference. Yeah. Yeah.
Yeah, that makes sense. It's just it's almost like an inductive versus a deductive view on how these
Yes.
problems are constructed.
Yes, exactly. Yeah. Yeah.
Okay, it looks like Nicole's having some technical issues, so I'll ask this on his behalf. What's your outlook on training and evals for low resource or data scarce coding languages?
Oh, that's an awesome question. I have there's a great there's another PhD student at Stanford who's fantastic, who's my year, Simon Guo, and he and his co-author Anne from Stanford with Azalea's lab, they released Kernel Bench like earlier this year, which also took off, and I think is a great benchmark. Recently, something they're thinking about is applying the SWE-smith paradigm to scaling up task instance collection for these kind of low resource languages, whether it's like CUDA kernels or, I mean, like, yeah, like sometimes like HDL languages where you're kind of defining like, hardware schematics or even, it doesn't even have to be crazy things, just looking at the distribution languages on GitHub, just things that are not anywhere near well represented as Python. For that, I I think if you look at, like, let's just say we went to a CUDA repository right now, you're not going to see a lot of issue PR pairs that exist naturally in the real world. Um, like for a variety of reasons, like that issue PR paradigm that SWE-bench leverages that Python has a lot of, it's just going to be much more scarce for the large majority long tail of languages. So I agree. I think it's a good question. It's a meaningful concern. For that, what I would say is that makes me very sort of like more bullish about using some of the non-issue PR pair strategies that we introduce in SWE-smith. So like synthesizing things via AST manipulations, or like, given this understanding of a language or a repo, how do you actually synthesize a lot of meaningful bugs? I think that's like I think that could be a great way to bootstrap like generating agentic trajectories for a lot of these low resource languages. And then I think you just try to get to a point where the agent can meaningfully kind of like, reason and code in these low resource languages. And then, potentially, there's some data flywheel that's out there that's oriented around code bases. There's a great paper from Meta that just came out called Code World Models, and they talk about a lot of strategies. Like a lot of them really, really resemble SWE-smith in terms of like how to take a code base or programming languages and generate interesting tokens or task instances. And especially for low resource languages, I feel like that could be a pretty successful approach. Yeah.
Yeah, makes sense. Yeah, it feels like that's a natural extension of things like mass token prediction, where you kind of get something from nothing by
Yes.
taking advantage of the innate properties of these functions or how code is written and can be executed.
Yeah. I agree
Okay,
more.
we're getting close on time. I don't want to take too much of your time. So if there are any last questions, feel free to put them in the QA feature. Alex, can you unmute and ask your question? I see that it came up.
Yeah, hi. Thank you, John, for the presentation. That was great. I just have a quick question. So, from your perspective, what's the most valuable kind of work that a university student could sort of do right now to contribute to the AI Evals ecosystem? Whether that's doing more research, working on tools, or maybe even creating my own benchmarks. What do you think is sort of the next steps for someone who's in university right now?
Yeah, no, that's a fantastic question. Instinctively, I think there's a couple of vectors. So in terms of increasing the number of repos or task instances, basically scaling up SWE-smith. I mean, this is something like I'm actively kind of shepherding along right now. Objectively speaking, like I know first impression, it sounds like a little bit grunt work in some sense, but I do think like a lot of the like very impactful early progress, like we'll kind of start with stuff like this. Like for example, we have SWE-bench multimodal exists, SWE-bench multilingual exists, multi-SWE-bench exists. The performance on all of those are 20 to 30 percentage points lower than SWE-bench. And so
I think we may have lost John. Raj, can you hear me? Is it my network?
Yeah, I think we lost John.
Oh no.
It's okay,
All
at
right.
least it happened at the very end.
Okay, while he's reconnecting, why don't I talk a little bit about what is going on with the community and where we're shifting the conversation. So Raj, do you want to talk at all about alphaXiv communities and how that's changing?
Yeah, totally. Yeah, it's been really awesome having, the AI evals, AI for Science among our other communities. We're just going to be moving over the real-time chat to separate places for each community, and I think we're going to kind of hand those off to the community leaders. So Ryan will be helping with coordinating a place for the real-time chat for our AI evals community, but we're absolutely going to continue to promote the talks and continue having these weekly seminars. So keep an eye out for that.
Hey, John, are you back?
yeah, I glitched out for a second, Yeah, I guess for people who are at Stanford, it's always the Stanford Wi-Fi that's kind of sus, but sorry about that. But yeah, sorry, just to kind of like really briefly continue. Sorry if I'm interjecting on anything. Yeah, I think data, I mean, like just because I think these frontier labs, like they're not going to release their data, just because that's kind of like where a lot of the value is for making these models better. And so I think that's absolutely an opportunity. There is a new eval that I'm hoping to release kind of soon, and so like that'll come out in the next 2 weeks, and so I think there we're kind of exploring more about like language models are not really struggling with bash or actions anymore. It's really like the reasoning or like how they're going about editing the code base that seems to be where there's sort of like more room to push. And so I think with that benchmark, like fingers crossed, like, happy to like try to like, get it to you guys when it's out there. But I think like understanding sort of, how do we push like better reasoning within the context of a code base, I think could be cool now that like action generation is like much more solved than it was a year ago. Yeah.
Great. Okay. We're getting close on time. Yeah, I just want to give a last comment that we're going to shift our conversation to the X Communities platform. So we're going to get that set up, and we'll have more talks in the future with people like Alex Gu from Live Code Bench. And so you can find out about when and how we host those on Twitter, and we'll send updates to Luma Blast as well. Maybe to close out, John, I just have a little bit of a naive, open-ended question. But last I checked, we still have, I think, over 1,000 issues for Django, and there's a lot of open source repos with lots of GitHub issues. Care to maybe speculate on why we see models that are so good and yet still have a lot of open source repos that have open issues like this that aren't being solved?
Yeah, I think that's a great question. This is, I guess, a little bit of more of my opinion and a hot take. So, I'm definitely not the arbitrator of truth on this, but yeah, I feel like with SWE-bench, like with the resolve rate, like we're kind of focused on whether it solved the unit test. And I do think in practice, people care about like how it's being done. I'll say one thing with the upcoming eval is that we do notice that like left to their own devices, if you just let a language model modify and maintain its own code base, the natural direction that it will kind of go towards is bloating the code base. Like it never removes files. It's almost like treats everything like a hackathon project where you have like V1, V1 final, V1 final, and these files are scattered all over the place. And so I think like now that models like even have a foothold in solving GitHub issues and tackling like real world development tasks, I think that maybe affords like a closer look into like how are they doing these things, because you have a PR pass the unit test and then you have a maintainer look at it and they're like, oh my gosh, it solves like, I mean, I think it's the old adage of like computers do exactly what you want them to do, that like it's kind of missing like the style and the context of the code base of what maintainers have done before. And it'd be really cool to see if the next generation of models can kind of incorporate this naturally. Yeah,
I think that's a great take. I don't know if that's a hot take, but makes sense.
awesome.
Yeah. All right, let's close out there. Thanks everyone for joining us, and looking forward to seeing you all in future talks like this.